Wow. All right. Yep.
This guy doesn't have to do both.
Good.
I'm not really sure.
So 15 degrees equals what over 2?
Should these rate?
No. 15 degrees equals what over 2? 30. Good. So put that. Cosine 30 over 2. So you've identified what theta is in the formula. What's theta?
Then you end up with 1 minus.
What's the formula say? Cosine of theta over 2. Alright, what's theta then? No. 30 degrees. I mean, you can make it radians if you want to, but you don't have to. So since you've written 15 as 30 over 2, and the formula is cosine of theta over 2. Theta is 30, so when you write the other side, you put a 30 there, and you know what cosine of 30 is.
Third step. And how do you determine the plus and minus?
What quadrant is 15 degrees in? Because that's your question. Wow. Alright guys, I'm going to try to catch up to you. So on 1A, you could say, I didn't give you enough room if you're not careful, but the first side has what on top? Cosine squared. The other side has what on top? How do you very quickly make that equal the top? You control what you can. You multiply the second dude by cosine over cosine. Then won't the top be true? I mean, this is kind of like my approach. I try this, when I can. If I notice something that I can very easily make the same as the other side, I do that. So let's see what happens if I do that. I know a lot of you guys have different approaches. You can write this as 1 minus sine squared and then factor it and cancel out a 1 minus sine and do all kinds of weird shit. Right? And it could take very long. But and the one thing I wanted to do today was to have you guys go down some wrong paths. You got to. I'm not going to take that away from you because you have to do that. And then we can come back in and say, here's what you look for and this is what you do. Here's what you look for and this is what you do. I can't make you a complete list of that because what could happen is the way I can't do my arms that long. Right? Is what could happen. But at least you have a few things that you know you can always try when you see certain things. So me, that's very obvious. That's cosine squared. Let me give this guy another cosine. So on the top I get cosine squared. What do I get on the bottom? What's cosine times secant? 1. What's cosine times tangent? Sine. Yeah, because tangent sine over cosine. Done. Check. Right, and again, I gotta be careful. I'm not doing this to make you feel bad. I'm not doing this to show off. Why do I know that really well? Because I've been doing it a lot. Right? It's easier when you teach the class. So that doesn't mean shit that I knew how to do that. It just means that I'm used to what to look for. Right? So now you guys kind of bank that. You kind of go, okay, I went through what I did, and now I know what to kind of look for to make it quicker. Now the other side of that is, I try to tell my students this, don't always try to waste a lot of time trying to figure out the best way to do something. Just kind of go with the first thing you kind of see, go with it. Because you want to get into it and try something, because maybe that'll work, and it's not the quickest way, but then you would have wasted time trying to figure out the quickest way. Don't do that. Alright. Did everybody find a way that worked for that first one? Alright. What about the second dude? And this is why I say don't immediately make things cosine and sine. Because what's 1 over secant? Because I can break this up. There's a single term on the bottom, so I can break that up. 1 over secant is cosine. And what's secant over secant? 1. Alright, that's pretty much as I can do on that side. So I'm going to look at the other side. What can I do with the other side? What can I do up there. Yes, 1 minus cosine squared. This is where, just because, what's this? So this is a longer expression than we're used to seeing for what we have to do here. We forget that this is really just 1 minus unknown squared. It's like 1 minus u squared. That's the difference of squares. So just because it's a trig function doesn't mean you can't factor it like anything. It's an unknown. It just has a longer name than I'm used to. Right? So I could factor 1 minus cosine squared as 1 minus cosine x, 1 plus cosine x, over 1 minus cosine x, bam, check. Cool. I like it. So you look for these kind of things. You can start to make a list if you want to. It's never going to be complete, but at least you've got a few things. If the bottom is a single term, you think about splitting it up. You think about doing that. Especially if the other side, well, the other side's a fraction also, but what the hell? That's a good thing to first try. You kind of with me? If the other side wasn't a fraction, I would definitely do that. That would kind of get rid of that fraction for me. I mean, you're kind of trying to make one side look like the other side. So you can think about the form it's in. Okay. And obviously you're always looking for your squares, because then those are identities that you can use. Is somebody tweeting that? Is that what it was? Dude, totally freak out for us. Now here's the other thing. This kind of relates to part E too. Notice how in part C and E you have pieces. You have a piece of the problem with one angle, and then the other things in your problem have other angles. This has an angle of x. These have angles of 2x. So it's never going to work unless you can make those the same. There ain't no way it's going to equal. The sides are going to equal. So that's where I start most often is. And look down here at part E. One trig function has an angle of x plus y. Does anybody else have that? No, so attack him first. Say, you're the freak. Let me make you look like everybody else so I have a chance to make things equal. Right? Don't take this as a life lesson, by the way. What did I learn from pre-calc? Well, beat the freaks up. Become normal freak. No, don't do that. So he's videotaping you. Mr. Waller said to do this. No.
You are videotaping.
Yeah. But yeah, I have the clarification on record. So what can I do with sine 2x? So now my argument, now my angle is x, just like the other side. And of course, what we're going to do, now here's where you almost can't go wrong, but there's a slightly better one to start with. Since you have a 1 plus, you maybe want to replace cosine 2x with the option that has a minus 1, so that goes away. Right?
2 cosine squared.
Good, so this is 2 cosine squared minus 1. So now your 1's go away. That kicks ass. And then what cancels here? I cancel a 2. Cancel 1 cosine. Sine over cosine is? Tangent x. Arrow check. Yay. See, that kind of thing tells me that you know you got to the end. A little arrow and a check. It's awesome. Show me that you know you got to the end. I love when people do that when it's not actually true. They're just like, maybe he just looks at this. No, it's good. I don't know why they do that. Alright. Now part D is really an obvious one to try. Whenever you have one side has separate fractions, the other side doesn't, you just put your fractions together. I mean, that's an automatic. Right? So how do I combine those two fractions? Yeah, so this guy needs a 1 plus sign. This guy needs a 1 minus sign. And on the bottom, I'm going to have 1 minus sign times 1 plus sign, which is
1 minus sign squared.
Yeah, just the opposite of that difference of squares we did earlier. And then on the top, what happens? Signs cancel. What the hell? 1 plus 1 is 2. That's crazy. 1 minus sine squared is?
Cosine.
Which is also known as? Done. How's that? Is that? Do you guys? You gotta go through wrong attempts to learn why they're wrong attempts and see it against something that's a better attempt or a more correct attempt, right? So like we said earlier, part E, I want to first attack this dude, and the only thing I'm going to do with him is I have something about cosine alpha plus beta or a plus b or whatever. Yeah, so that would be cosine x,
Cosine y.
because he's the asshole, right?
Minus sine x, sine y.
Good. And notice, now this is even more, I have a fraction on one side and the other side no fraction. So how many terms do I have on the bottom of this fraction? One term, which means I can split them up. So if I put, let's see, let me just write it all out. So obviously here, the cosine x's go away. What's cosine y over sine y?
Cotangent y.
Cotangent y, that's crazy. And over here, the sine y's go away. And what's sine x over cosine x? Tangent x. Arrow, check, yay. Let me stop there for a second. Oh, I went too fast there. So I split that fraction up because there's a single term on the bottom. People get a little overly enthusiastic and split it up even when there's more than one term on the bottom. It sucks. Don't do that. That might work sometimes, but normally no. Blah, 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 and then I just canceled what I could, rewrote it using basic identities. Bam. How's that? Is that cool? All right, so let's get to these. It's not hard to do, trust me. I mean, sometimes I'll have a problem that I'm trying that I hadn't done before, and I just start with the hardest way to do it, because that's the first thing I see. And that's why I'm like, if you see a better way, let me know. Because just because I'm teaching and you're sitting there doesn't mean you don't have a better way to do a specific problem. Just give it to me. You're like, why couldn't you do this? Oh, sweet, thank God, yes. You saved all of us some time. Now this dude, and this is kind of nice. I wanted to give you this problem so you have the right way to look at this. The angle that I'm trying to work with is exactly half of an angle that I know. So I want to use the remarkably well-named half angle identity, right? So the half angle identity has cosine theta over 2, right? And then on the other side it's got in terms of theta. So I have to first identify what theta is. Theta is not 15. Theta is what I get when I rewrite this as something over 2. And of course that was the 30 degrees we talked about a second ago. So now you know theta is 30 degrees. So when you write the other side, two things. 15 degrees is in the first quadrant, so it's going to be the positive option, right? That's how you pick the plus or minus. It's just where's the angle that you're working with. That's what's going to tell you what the answer is. 1 plus cosine of 30, because that's what theta is, over 2. And what's cosine of 30? Square root of 3 over 2. Let's see. Let me do this in a few different ways. And if you left it like that, I wouldn't take points off. I'd point out that there's a couple things you could do. You have a fraction inside of a fraction, so you can do what?
Cancel the 2.
Yeah, so multiply top and bottom by 2. You can't cancel the 2's.
Right.
You can multiply top and bottom by 2, so you'll get rad 2 plus rad 3 over 4. And what's the square root of 4? So the top is rad 2 plus rad 3 over 2. Kick ass. Funkadelic. So yes, you do have rad inside of a rad. These things happen, yes.
Could you also do cosine of 45 minus 30?
Oh, I love it. Kick ass. All right. So if you have, when I made that problem, that's what I intended was a half angle, which you can say, okay, this is cosine of 45 minus 30. All right, cool. Let's see. Now this is kind of neat. You're going to get an entirely different looking expression, right?
Yeah.
But if you put both of them in the calculator, they come out the same, which is weird. So how do I rewrite this?
Cosine of 45 and cosine of 30.
Good, because he's all, I'm me first. It's a minus, so cosine says,
Plus.
screw you, it's a plus now.
Sine of 45.
And then sine finally gets his turn over here. Cosine of 45 is? Rad 2 over 2. Cosine of 30?
Root 3 over 2.
Rad 3 over 2 plus sine 45. Sine 30 is 1/2. So you get rad 6 over 4 plus rad 2 over 4. You with me? which does not immediately look like that dude, right? But there is some slightly freaky stuff you could do to this to make it look like this, believe it or not. Now, if you put both of these in your calculator, they'll come out to the same answer, and then if you put cosine of 15 degrees, it'll match with both of those. Cool. So depending on, sometimes, I don't know, I haven't checked this out with the book, with the answers in the back. It depends on the way they choose to do it. I don't know if they list both possibilities, or they just give you one. So don't immediately freak out if they have something different in the back. Just put it in the calculator to see if it comes out to the same thing you got. You might have just picked a different way to do it than they did. Cool. Let me get a fresh. So we got that. Is that decent? Okay. So this guy, this is cosine squared of some angle minus sine squared of the same angle. So it's like somebody pointed out, if those weren't both pi over 8, if one of them was like pi over 12 or something, I couldn't do what I was about to do. Because the identity that that's related to requires them both to be the same. And what is cosine squared theta minus sine squared theta? Good, cosine 2 theta. So this is cosine twice pi over 8, which is cosine of pi over 4, which is right 2 over 2 done. Sweet. Oh. Dude, you learn. Dude, you learn. And this kind of thing happens more often than you might think, just because there are angles that occur in a lot of different fields that are related almost to angles that we know. And there are times, I know that you're saying, well, I can just plug in the computer or something, but there are times that you want the exact expression, not a decimal representation. You want the exact expression. Now this one freaks everybody out. Exactly, because what is the inverse tangent of something? What is it physically? It's an angle. So this is sine of 2 angle. Sine of twice an angle, right? So inverse tangent of something is an angle. So that says sine of twice some angle. And what's sine of twice some angle?
2 sine theta.
2 sine angle, cosine angle. So you can't just double the sides of your triangle, because then effectively it's the same triangle, because it would reduce back to itself. You can't do something that simple. This tells me something about theta. This is asking something about 2 theta. Those triangles don't exactly relate to each other nicely in any way. So you want to rewrite it in terms of the angle itself. This dude is talking about theta, right? That is theta. So I want my question asking me about theta, because that's the angle I know everything about. What's the triangle I can draw for angle theta? Anybody make it this far? If inverse tangent of 1 is 3 over 7, how can I draw the triangle?
3, 7, 58.
I love it. So 3 is where?
Right there.
Like that. And 7 is there. And then you do the Pythagorean theorem, you get square root of 58. So then what's the sine of... Now, what do I need then to answer the question? I need sine of theta and cosine theta. So this would be twice, what's sine of theta?
3 over rad 58.
Yeah, 3 over rad 58. We'll see if we have to do anything with rationalization in a minute. This is why you don't rationalize till the end. You'll see what happens. What's cosine of theta?
7 over rad.
7 over rad 58. So on the top I get 2 times 3 times 7 is 42.
Oh.
And on the bottom I get
58.
58. And of course that reduces to something. Sitting there like, my battery 2 problems ago, man. That's crazy. Alright. So there are, in fact, I took all of these problems out of the chapter review. All these problems are in the chapter review in the book. So this is not something I just made up. It's not going to be it's in your homework. All of these problems are in your homework. Don't get too excited. We're not leaving. Just going to stop you in case you're starting to pack up. All right. So any questions on that sheet?
On number 2, part C,
Would you always like recommend you start out with a triangle and a solid? Like the way you...
Yeah, the first thing I do is I identify that this is going to be twice sine, angle, cosine. And then this is the angle, so it sets up the triangle. And then I plug what I need into there.
And you're looking at it, tangent is sine over cosine, and just plugging in the numbers to that, and then doing the...
Well, we have to draw the triangle so I know the right ratios to put in here.
Right. And then when you do that, then you do the theorem, and then you plug in from there.
Yeah, so here I've got the triangle drawn from inverse tangent.
Mm-hmm.
And then I just plug what the sine is and what the cosine is, I plug it in. And then just work it out. Yeah. So I never really use this.
Right.
I use what it is in terms of theta. Because I can't do shit with this. I don't know a damn thing about twice theta. But I know everything about theta.
How do you know it's a right triangle? Or does it not matter?
Okay, I love that question. You ready? How do I know it's a right triangle?
Because you drew it?
I love it. Because I put that little box there. All right, next question. No. What, inverse tangent of 3 over 7. And this is part of the reason why I said this triangle doesn't have to exist. This triangle could be nowhere near the mind of the person who has this problem. But I can always draw a right triangle that's directly related to tangent, because tangent is fundamentally defined using right triangles, right? So even though tangent applies to things, now we know that it applies to things that aren't necessarily right, I can always, right triangle, I can always take this expression and represent it in the most basic way I can, and then use it, right? So this, I need sine theta. Well, I know that tangent theta is 3 over 7. So I can figure out what sine theta is. And the triangle is a nice way to do it, just so I can see all my sides. How we do and so forth. What I'm saying there's actually a whole other way to do that without drawing this triangle. Using identities. But there's no nice identity from tangent and to sine, is there? Right? So that's why this triangle method works no matter what. Okay, maybe. That was a good question. That's why I know, because I can always draw the most basic idea of what inverse tangent means, which is related to the sides of a right triangle. Kick ass. Cool. So, I want to get just a little bit into the next section. Oh, that's the wrong one there. Believe it or not, when I say the next section, do you guys know what section I'm talking about?
8.1.
Sure, let's do it. 7.4. 7.3 was the double angle and the half angle. There are a couple other identities in that section. That's nothing I'm making you memorize. If they reference it in the homework, you have it right there. It's just plug and chug. You don't have to understand where it came from. You don't have to memorize those other ones, right? Anything below the black line on that page I gave you?
Yeah, on the quiz, because on the home there was the area of the triangle, which is the Aaron formula. Do you have to know that?
Oh, no. That's just an interesting historical footnote that I wanted to give you a problem on. But you don't have to know that one. I'm not even going to... But it's kind of neat when you look back at what people did before there was a damn thing. No internets, no calculators, right? Not even nice paper, right? Some rough-ass paper, right? But they did a lot of shit. They did a lot of neat stuff back then.
Do you know how to use an abacus?
I used to. When I was a lot younger, they showed us. I have a Himalayan calendar in my office that people think is an abacus because it looks kind of like that, but I couldn't. I don't even remember how to use the slide rule. I feel bad.
What?
You guys ever heard of
Now, that was perfect.
slide rule? Was the way that people used to do calculations before calculators were invented. So it's a kind of a nifty manipulation of how to place numbers, and you just move it, you slide it. I have a circular slide rule, which is kind of neat, and I've already forgot. I can just do some really basic shit with that, but it's amazing what you can do with slide rule. So Google slide rule, right? It's sort of in the same camp as 8-track tapes, I guess. Right? 8-track what? Oh yeah, 8-track tapes.
Wasn't that long ago?
Alright. So let me give you this. Let me see what you guys think about this. So section 7.4. Let me just give you a prompt. You can do this. Now this is kind of semi-evil, but not really at all evil because I'm not grading this shit. I'm not going to see what you're going to do. Solve that.
You want us to put this like into a triangle? Do that?
Nope. Not necessarily. Do what you have to, I guess. But you should know. If you only get one answer, you're wrong.
Oh, okay.
If you only get 11 answers, you're wrong. But at least get one answer. Let's start there. Get the one answer that's obvious. Somebody, I got 11 answers. I really don't think that. Well, what's the basic answer to this?
30 degrees.
So I can write it as 30 degrees, but what way do you think I want you to write it?
Alright,
Let's do it there. So I can write this as degrees, but I really want us to get into that radian thing all the way. Now this is not correct only because there are more answers. There's a couple more. Well, maybe an infinite number more. Right? Because sine of x, if you look at the graph of sine, how often does it hit 1/2? There, and there, and there, and there, and there, and then the other way, only the other way too. So there's an infinite number of places where sine hits a 1/2 horizontal line, right? It's an infinite number of places where it's 1/2. So how do I represent that?
That would be.
So we got this pi over 6 here, right?
You've got. It's. God damn it. Plus. It's pi over 6 plus 2 pi times m, I think is it?
Or n, sure.
Yeah.
We'll use k. Just because the book does, but you can use either one. Now, real quick, now, because how far do I have to go until I hit this again, basically, until I hit that angle again? 2 pi. And based off of your homework that you've done on coterminal angles, they're separated by 1 revolution, which is 2 pi, right? Is that cool? So obviously, if I add a single 2 pi to this, that's another answer. If I subtract 2 pi from this, that's another answer. If I add 87 2 pi's, that's another answer. So that's where the k comes in. So it's just some multiple of 2 pi added to this. Right? So in a way, we're halfway done. We don't have all the answers yet. This infinite number of answers is not good enough. Where else in 0 to 2 pi, one answer is pi over 6. That's one base answer. There is another base answer. Where else is sine positive?
5 pi over 1.
Yeah. I love it. A pi over 6 reference angle back here, right? So there's a whole other set of answers based off of 5 pi over 6. So what you do is you find all the answers that work in 0 to 2 pi, and then you start adding rotations to capture all the other answers that are coterminal with those. Let me say that again. You find all the answers in 0 to 2 pi. Those are your base answers. And then off of those bases, you build rotations. So you can pick up all the other answers. Does that make sense? Because sine goes forever. It always does the same damn thing forever.
So you're telling me you're going to have 4 sets of infinite answers?
Not 4. 2 sets, yeah. Because this is it. If I try to go another pi over 6, that's where sine is going to be negative. I like it. How are we doing so far? So that's the kind of thing. You have to pay attention to the questions. Sometimes the questions will say, find all the answers in 0 to 2 pi. In which case, that and that would be it. Sometimes it'll say, find all the answers. In which case, you have to write it like this. This represents all the possible answers. So let me ask you this. If k equals 1, let's start with it. If k equals 0, I get pi over 6 and I get 5 pi over 6, right? What if k is 1? What do I get? Which is? K is 13, 5, or 6. Good. 13, 5, or 6. And over here I'll get 7, 5, or 6. Let's do one more. So if k is 2, what do I get? K is 2. Now you should be able to do it very quickly. How did I get from here to here? I added 12, basically, right? So add another 12.
25, pi over 6.
And here I'm going to add another 12.
29.
Alright, cool. So sometimes the questions will have a third option is they'll say, give me 6 answers. There's 6 answers. Or you can make k negative if you want to. You can go backwards. Yes, sir?
Is there a way to express those as a single?
No. I like the way you're thinking. Because we will see in a minute that you can do it in a single expression. But how far apart are these? That's a good question. I like that question. Remember, this angle is 5 pi over 6. How far apart are these? No, don't guess. How far is this angle? What's this angle really? 5 pi over 6. Not the reference angle. That's 5 pi over 6. This angle is 5 over 6. How far apart are they?
4 pi over 6.
4 pi over 6. Cool. So I could say pi over 6 plus 4 pi over 6 gives me another answer. But I can't. But then how much do I step to get around to the next answer? How far apart are those? Oh, shit.
7 pi over 6.
Let's see. This is pi, right? This is pi here to here. Plus another pi over 6 plus another pi over 6. So it's pi plus pi over 3. Something like that, yes. Okay. So I really want you to... I can't represent both of these in a single line because the steps I have to take are not equivalent. I can't say plus k times the step size because the step here is not the same as the step there. And of course that would be 2 pi over 3. Right? If you reduce this as 2 pi over 3, what's 2 pi over 3 plus 4 pi over 3? 6 pi over 3, which is 2 pi. That's why the other part was 4 pi over 3. That's the rest of it, right? But that's a really good question. But you have to give me both of it. You can't condense it to one. Let's do a problem where you can, and then we'll probably call it.
Based on what you've already said, they have to be, what, 180 degrees apart, like that part from each other?
Here we go. Ready? Thank you. So what's the first step, do you think, on this problem? Take a square root, keep gas. Take a square root. When I take a square root, I better put plus or minus. See, that never changes. Plus or minus 1. So where's tangent plus or minus 1? At all the what? What? Tangent's 1, where? What angle? Pi over 4, 45 degrees. So it's positive 1 at pi over 4.
Negative.
Pi over 4 past pi, so 5 pi over 4, right? And it's negative at 3 pi over 4 and
11?
7 pi over 4, because that's pi over 4 away from 8 pi over 4, which would be 2 pi. Alright, so hopefully you continue to do this, which is good, because you have to get decent at manipulating your radians, knowing what it represents based on the fact that you're 1/4 of a pi away. You should be able to come up with that pretty quickly. Now what's nice here is all of these are separated by how much? Kind of gave it away, but... yeah, right? So I can actually represent all these answers. There are like 4 base answers, but I can represent all the answers off of this. Because I just had to go 90, 90, 90, 90, 90, 90, or the other way around. So it'll be plus... what's 90? Pi over 2. So plus pi over 2 times k. Because they were equally spaced from each other, I can capture all of those answers in one expression. Were these equally spaced from each other? No. No. So I can't capture them in one line. So it's a really good question. I like it. And that's fun. Oh, wait.
So a non-equal plus or minus when covering plus.
Say again? Oh, why did I do that? That's my bad. Because K, actually, I always forget. K should be negative. Good. Some books put the plus or minus because they put N. N normally means natural number, 1, 2, 3. K is an integer, so I just have to put a plus. So I got to be careful not to.
Sine of x equals negative half. How would you do that?
Then that would have been these outputs.
Okay, but you still
That would have been your bases there, and everything else would have been the same.
plug in the negative k.
Of course. Because I could, if I had this, my two answers would be this, right? So negative 5 or 6. And then I could represent that just 75.
How would you write that up?
Yeah, so it'd be negative 5 or 6 plus 4. Because I can start here and add, or I can go backwards of revolution. So it's just the idea, if I move one revolution forward or backwards, I end up in the same place. So it's almost, of course it's going to be the right answer. It's the same damn place. So that's why I can always do this for sine and cosine, because the period of sine and cosine are
Alright, that,
yeah, just shoot her name and say I'm interested and I'll show it to you next.
Alright.
I like it, good. I like it.
So how come we can't, so how come for this one, it's plus
One
1
line.
over 2 and 1 line, but this one is
Because how far do I have to go from pi over 4 to the next answer?
2 pi.
Pi over 2. And how far is the next answer? Pi over 2. How far is the next answer?
Pi over 2.
So all the steps are the same size. So if I take one step of pi over 2, I'm to this answer. Another step of pi over 2, then this one, if I take one step of 2 pi over 3, I'm to that answer. Then I take a step of 4 pi over 3 to get back to another answer. They're not the same size. I can't represent it in a single line. I cannot represent these two in a single line because I have to go a different amount. I could represent this in one because there's the step size, one step size. So I can do one line. This would be 2 step sizes. So I can't do one line, I have to do 2 lines.
Okay, but it's still pi over 2 because...
Well, still 2 pi. Because from this one I got 1 revolution, and this one I got to go 1 revolution.
Okay, cool.
Will it be quiz Monday?
Quiz Monday, yeah. 6-4, 6-5, 6-6, 7-1. Yeah.